Good afternoon, dear colleagues. Nice to see you here. And today, I'm very glad to announce the talk of Jim. Jim is a PhD student of the third year in the group of Pavel Belov. And today he will present a work about manipulating the electromagnetic field in wire media resonators for axion detection. So Jim, the stage is yours, and you're welcome to ask the questions during the talk.
Good afternoon, everyone. Thank you so much for the kind introduction. So in this talk, I will be talking about a strategy to improve the field homogeneity in wire media field cavities, which is important to enhance axion detection. So the outline of this talk is the following. First, an introductory part, including a motivation and some previous works about this line of research. Then the main part focus on the strategy that we are proposing, including an effective boundary condition for our wire media cavities. Then the application of that boundary condition to a square cross-section cavity, later to a cylindrical cavity, and finally to a hexagonal cross-section cavity filled with a honeycomb wire medium, which has an additional result is that we can measure the plasma frequency of such cavities. And finally, some conclusions and perspectives. The motivation is the following. Franz Wilczek in the 1978 proposed the action, and particularly one of the interesting details about this particle is it is a potential candidate for dark matter. The characteristic of this particle is that it has a very low mass. It has extremely long decay times. It weakly interacts with matter, and it also weakly interacts with electromagnetic fields. So if we want to check how it interacts with electromagnetic fields, we can check these details in the Maxwell's equations. So in the Maxwell's equations, we are going to have two extra terms coming from effective charges and effective currents. We can understand them as effective charges and effective currents in our Maxwell's equations. Particularly, this A denotes the axion field. And by definition, the spatial derivatives of the axion field are small in comparison to the temporal ones. So the term that will matter for us for the detection of the axion will be this one that includes the temporal derivative of the axion field. And we can see that it is proportional to the magnetic field, to an external magnetic field, and also proportional to a coupling coefficient. Particularly, this coupling coefficient is really small. So the experiment to detect the actions would require high magnetic fields in the order of 8 Teslas or bigger. Another condition that requires an experiment to detect the action is to have a control environment. So that control environment has been proposed to be the cavity haloscope, a simple microwave cavity. So with a microwave cavity, we can resonate that signal coming from the action inside of our cavity in the whole volume. It has the advantage that as it is a resonant effect, we can increase the signal. One limitation that it can have is that it requires large volumes for the detection. We need a large region for the detection of the action. But if we consider that the action mass could be in the range of the gigahertz, 10 gigahertz or around it, we will have really low wavelengths. So the volume of our cavity to achieve that resonance would be really small. So if we have small volumes, we are decreasing the chances to detect the action. So people have proposed some strategies to try to increase that volume. One of those strategies that looks simple, for example, is introducing a range of cavities, several range of cavities resonating in the same frequency, and then we can get a higher volume. Other strategy that has been recently proposed is the use of metamaterials, particularly wire media field resonators. So with this wire media field resonator, we have the following advantages. We can match the action with the photon inside of these cavities. But in addition, we can have control of the resonant frequency of our cavity by changing the plasma frequency of the wire medium inside. And this plasma frequency can be easily tuned by changing the wire radius or the wire spacing, or both, right? And this is the advantage. So it will be independent of the volume. We can have high volumes and the resonance will not matter in the volume, in the size of the cavity, but in the space of the wire medium and the radius of the wire medium. Another characteristic is that in the experiment, if we want to increase the chances to detect the action, we need to work in cryogenic temperatures, and as I said at the beginning, high magnetic fields. Those conditions are not easy to deal for any material, but particularly for the wire medium, we don't have problems in these hard conditions. At least now we don't have big problems. It is still an active area to check how this wire medium is behaving in these extreme conditions. So you can check more details here in this alpha link. This alpha is a consortium, an international consortium that is looking for the action, having as main component our wire media field cavity. So some details about the wire media resonator that are important for the detection of the action. The parameters concerning the cavity are the following that are relevant for the action detection. We have three of them. We have C, which indicates the form factor. It will be the main focus of the talk. We have the cavity volume. As I said before, we can have really large volumes without problems in the wire media field cavities, and the quality factor in resonance for the resonant mode of our wire media cavity. The form factor, particularly when we are assuming an external magnetic field along Z, along the axis of the wires, has this shape. And it basically indicates how uniform is our field inside the cavity. It's a measurement of the field homogeneity inside of our cavity. Particularly, it has been studied in the wire media field cavities that the mode with the highest form factor is the fundamental TM110 mode. And this mode has a form factor of 0.62, indicating that in the axial direction, we have a uniform field. So there is no way to optimize it more. It's already uniform. But in the transversal section, we have a sinusoidal profile, right? So this sinusoidal profile is the one that is limiting our form factor. It is becoming our form factor equal to 0.62. If we compare with another cavity haloscope and other strategies, we can see the following values for the form factor. We have a value of 0.69 for the empty cavity. This is just an empty cavity. We already know with the limitation that the resonance depends on the cavity size, but with this form factor of 0.69. And there are several proposals, but among them, there is one that highlights a high form factor of 0.8. This is the coaxial type cavity with hexagonal cross sections. This one has a high form factor for the fundamental mode, but it has the limitation that the field is mainly confined in the intermediate region between the metals. So if we seriously include the inner metal, it is a limitation because it's a useless space. Yeah, so this value should be actually lower. So let's try to explain how we are gonna optimize that form factor in the wire media resonators. We have the following strategy. Typically, when we have in our cavity as only content the wire media, we have the cosinusoidal dependence that I mentioned before, so it makes the transverse profile limited. We have the sinusoidal profile. Then, if we start to include, in addition to the wire media, an air gap region, this air gap region will start to change our transversal component of the wave vector. So when this transversal component of the wave vector start to decrease, we start to increase the field homogeneity. particularly when this transversal component of the wave vector becomes 0, our field will become completely uniform in the wire media region. And this condition is achieved when the air gap region is equal to lambda over 4. And to explain this idea, let's start with a one-dimensional model. So in a one-dimensional model, we have the following scenario. We are gonna ignore the variations of the field along the y and z direction. We have the electric field that is in the z direction perpendicular to this plane. And we are gonna consider two regions. Region number 1, in which we have the wire media. Region number 2, in which we have the air gap. And at the end, this air gap is bounded by a perfect electric conductor wall. So to deal with the wire medium, we are gonna use an effective model for the wire medium, which treats the wire media as a uniaxial media. Particularly in this uniaxial media, the relevant component of the epsilon is the Z1, this epsilon Z. So this epsilon Z follows the dispersion of a plasma, right? We have this dispersion of a plasma, particularly as we are focused in the mode with the highest field homogeneity, we are not including special dispersion effects for this fundamental mode. And if we want to check the field inside of our cavity, we are gonna have the fundamental behavior with this cosine for the core region or the wire media region. And to satisfy the boundary condition in the PEC, we have this sinusoidal dependence. We can check that when we evaluate our x in d half plus g, this sinusoidal argument will become 0. So our field will satisfy that boundary condition in the metal. Particularly, we can also, with the Maxwell equations, we can get the magnetic field, this y component of the magnetic field. And we can also analyze the dispersion of our wave vector in the wire media region and in the air gap region to get these components of the wave vector in every region. And we can also derive a wave impedance in this boundary between the medium number 1 and medium number 2. This wave impedance gives an idea of what kind of boundary our wire media will be experiencing in this interface. So we have two particular cases for this impedance. When the air gap is equal to 0, we can analyze directly, and we have the trivial case of the perfect electric conductor boundary. And when the air gap is equal to lambda over 4, we can check here in the denominator that our denominator will go to 0. And with this condition of lambda over 4, our denominator will go to 0, and we are gonna achieve an impedance that tends to infinity, which creates a perfect magnetic conductor boundary condition. Yeah, so we have a perfect magnetic conductor boundary condition in this interface between 1 and 2. Our electric field will be unaffected, and it will allow us to get the uniform field that we are looking for. Sure.
It is a stupid question, but the field must be continuous at the plane number 1, and you have cosine and sine, but at the d over 2, it should be continuous, no?
It should be continuous, yeah. In the boundary between 1 and 2, it should be continuous. Actually, that continuity is that the one that we use to get the dispersion relations, and at the end to get which is the resonant frequency at the end, because that resonant frequency is being affected. It will be mentioned in the next slides. In this 1D model, we are not interested because actually in the reality, we have square cross-section cavities or circular cavities. So later we are gonna see the match. Yeah, of course, we should have these coefficients to match each other. In the boundary, we should have continuity.
Okay.
From each formula, it follows that the distribution is homogeneous.
The distribution is homogeneous so far. We have this impedance boundary condition, this wave impedance, that is indicating which kind of boundary condition we are imposing to the electric field. So we have these two cases. So far, we haven't mentioned particularly why it will become uniform, but we have this hint that we are going to impose a boundary condition that push the field to be zero in the boundary when we have G equal to 0, and leaves the field uniform when we have G equal to lambda over 4. Yeah, actually, we can also plug these values into our fields, and we are going to see that this argument in the cosine becomes 0. The argument in the cosine becomes 0, and the field becomes uniform in the wire media region. Yes, and I'm gonna particularly show the results in the 2D case. In the 2D case,
but what becomes 0? Kx1 number becomes 0 under the cosinus function.
the
k vector becomes 0 in this case, or what?
Yes, what we have in the condition of G equal to lambda over 4 is two details. The epsilon will become 0. So if the epsilon becomes 0, we have this term kx1 equal to 0, so the field becomes uniform in this case. Yes, so that's particularly the detail. I have a plot in the next slides about this epsilon, how it is behaving.
Okay.
Also about this impedance, how it is behaving. So in the square cross-section cavity, to address the problem of the square cross-section cavity, we are going to make an assumption. As in the study of dielectric waveguides, first approximation can be the Marchetti-Ellis method that basically ignores the corners of our region. So we can approximate the solution of a 2D model, a 2D problem, with the combination of the solutions of the 1D problem, ignoring the edges. Yeah, so basically we are going to have an inner region, number 1, including the effective wire media, and an outer region, including the air in the Y and X direction, ignoring the corners. So in this scenario, we have the following. We have the fundamental TM mode. In the core, we are not focusing on the individual components here because it is symmetric. We have a square cavity, so we are calling this transversal component the same for X and for Y. And we have the other components of the field. So when we match these fields in comparison to the field in the air gap region, we can get this dispersion equation. So this dispersion equation includes the transversal components in the region number 1 and in the region number 2. If we want to relate them, we need to check the dispersion in every medium. Particularly in the effective wire medium, we are going to get this dispersion relation because of the uniaxial media. And we also have in the air region, for example, in this region that we have here to the right, in which the number 2 is placed, we get this dispersion relation. So with these equations, we can solve our, we can solve our problem. We can get a wave number. That wave number will be associated with the resonant frequency. And then we can plug these values into our electric fields, and it will allow us to get the electric field profiles. This is the idea. So there is an extra detail here. We have been mentioning that we are using an effective wire medium. So we need a plasma frequency for that model. We realize that it is depending on the wave number of the plasma. So there are two ways to try to determine it. Make it analytically with an analytical model, or take it numerically also. Make a simulation of an infinite wire media and get the plasma frequency from the numerics. The path that we choose for this work is the one that uses an analytical model to calculate that plasma frequency. Particularly, we use a quasi-static approach by this author, and we can also see that it was compared with the numerics in another work of my colleagues. And we see that there is a good agreement. Actually, we will be working in this regime in which the radius of the wires divided by the period is equal to 0.05. And in this regime, we can actually see that several analytical methods are matching well with the numerical one. Particularly if we go to the details, here this QMAR analytical model is the best one. So that's why we decided to use that analytical formula, but it's also possible to use the numerical one. So some preliminary analytical results from that model. We mentioned the impedance that we have in the boundary of the wire medium. So we can see that this behavior, that when the air gap is equal to 0, we have the perfect electric conductor. And when the air gap is going to lambda over 4, we start to get this condition of our impedance going to infinity, indicating a perfect magnetic conductor. If we check this transversal component, which was important and which was in our expression for the electric field, and to see how it is uniform or not, we can see that when we have the G equal to 0, we have a K component of the vector that is bounded by the walls, right? It will depend on the length of the cavity. But when we start to include the air gap, and particularly when we put the lambda over 4 gap, we are going to have this transversal component of the wave vector equal to 0. So it was inside of the cosine function. So when we have 0, this cosine function will be the maximum possible and will be uniform along the transversal section of our wire media region. And if we check the effective epsilon, we can see that the lambda over 4 condition, this epsilon becomes 0. Particularly here, we have that condition of the epsilon equal to 0. So let's compare with some numerical results. Numerical results can be simply obtained in a 2D model in COMSOL, including the wires, right? So we have the following behavior. When we have the air gap equal to 0 in the analytical model and in the numerical simulations, we can see that this transversal profile is a sinusoidal one. When we include the lambda over 4 idea, the electric field is perfectly uniform in the wire media region. For the analytics, in the numerics, we of course are appreciating the field drops due to the wires. We have some field drops in the wires, but in the other regions, it looks uniform. So it's quasi-uniform in this numerical analysis. And if we check further, if we check more details about it, other cases, I mean, of the air gap, if we check other cases, we can see this plot here about the electric field. It will be a line plot along the center of the cavity. And we can see here several cases of the air gap. So we start with the sinusoidal profile going to 0 at the edges. Then we go to the case of the uniform field in the wire media region when the G is equal to lambda over 4. And then when we overcome that value of lambda over 4, we start to get a behavior in which the electromagnetic field start to be localized close to the cavity walls. This is the behavior of the gray curve in our chart. Yes.
In the resonators, you consider what happens to the ends of the wires. Are they soldered to a metallic wall? I mean the plane which is parallel to the slide. Yeah. Like in the conventional wire medium resonator from older works, there was like open end of the wires at the extremities, and therefore also some open boundary condition was applied, and the mode could be also uniform along the wires.
Yeah,
While you have shown some designs of the resonators which are soldered from all sides, also from this perpendicular direction.
yes, maybe you are going ahead in the talk because it will be mentioned later, but yes, you are right that it's important to assure the uniform field in the axial direction that I mentioned actually at the beginning. It's needed to have an electrical connection between the wires and the top and bottom cavities, walls. It is because, yeah, if we don't have the electrical connection there, we are going to have some capacitive effects between the wires, the top of the wires, and the top plate and the bottom plate. And it creates homogeneity effects, even though those effects can be really problematic. And in the experimental realization of these axion alloscopes in this alpha consortium, we have experienced a lot of troubles there because when you need to make a tunable cavity, we are gonna need to include a mechanical system there. So having an agreement between the mechanical system and the electrical connection is a real challenge. So we actually have seen in several of our prototypes that detail that if we don't have the electrical connection, the field homogeneity in the axial direction actually drops.
But when this effect happens, when you change this gap and you affect homogeneity along X, what happens along Z direction?
It's unaffected. It is, if we have the ideal condition in which the wires are connected to the top and bottom plates, it's unaffected. The axial direction is not changing.
So it's still homogeneous.
It's still homogeneous.
Okay,
Yeah,
thank you.
it's still homogeneous.
I also have a question. Could you please explain the physical purpose of such an oscillating behavior of electric field distribution along axis in numerical simulation, like dotted points?
Oh, you mean these ones? These?
No, on the plot, on the
Oh,
right side, yeah.
this oscillation behavior. Yeah, it's a good point actually, because I mentioned that we are located just at the center of the cavity, right? So in the center of the cavity, it's supposed that we don't have the wires, right? We have this line approximately with the laser pointing that I am indicating. So it's supposed that we don't have wires in that region, but actually the field is dropping in those wire media regions. So it is also affected in the regions around those wires. So we can see that a small effect of the wires that are around this point. So this is why it's oscillating. If we would focus in a line containing the wires, the field would drop completely to zero in those regions. Yeah, because they are considered as perfect electric conductor. Okay, so let's continue with the parameters that are important for the axion detection, the ones that we mentioned before. First, we have the quality factor, that is a parameter that basically it's slightly improved with this λ/4 idea of the air gap, but it's not considerably changed. The order of magnitude keeps the same. Then if we check the form factor, which is the one that measures the field homogeneity, we can see the biggest advantage of this strategy. We have the following behavior. Here, in these next two plots of the form factor and the resonance frequency, we are gonna have three curves. The solid one coming from the analytical model, we have two numerical results. One numerical results indicating the physical wire medium. It means this numerical modeling includes every wire with the radius of the wire and everything. And another numerical results in which we in COMSOL are modeling the wire media as an effective one. So we are gonna introduce the dispersion of this effective wire medium inside COMSOL to reproduce this result following the stars in the plot. So we have the following behavior for the form factor. When we compare the analytical results with the numerical ones, we can see that they are slightly higher than the physical one. Yeah, because they are not including the field drops in the wires. That's why they are always a little bit higher. But they follow the trend. All of them follow the trend that we have a maximum form factor around the λ/4 distance for the air gap. Particularly, it is coming from 0.62 in the physical wire medium to 0.89 when we have the maximum value. So we can see the improvement there. Yes, so this is related to the form factor. And in the resonant frequency, we can see that our three results match really well. It doesn't matter the presence or not of the wires. So the important detail here is that with this strategy of the λ/4 gap, we are also targeting exactly the plasma frequency. So the resonant frequency of the fundamental mode of the cavity will be the same as the plasma frequency. So it can be used as a strategy to measure the plasma frequency of a wire medium by using a cavity like this one. It's a side result. And maybe a question that can arise is that we have a really bad agreement over the value of λ/4, right? So it is happening because in our 2D model, we made the assumption of ignoring the corners. So when the corners start to play a key role, I mean, when the electric field starts to be localized closer to the corners, our validity of the 2D model starts to decrease. And this is what is happening here. We saw that in the plots of the electric field that above that condition of λ/4, the field starts to localize close to the cavity walls. So when the field is localized close to the cavity walls, our results start to decrease. However, we can result that still the numerical results coming from the physical wire media and the effective wire media have a good agreement yet in that region.
Can I ask a question about previous slide? Did you consider the air gaps in the calculation of form factor, or you use only the area with wire media?
Yeah, that's a great question. At the beginning, I wanted to calculate just the wire media to highlight even better the result to get higher values. But like being coherent with the experiment, it's needed to calculate the whole volume, to take into account the whole volume. So this form factor includes everything, the whole volume inside the cavity, including the air gap. That's why we reach 0.89, and in the theory, we reach also a value of 0.90 something. In the ideal case, we should get 1 for the analytics. Yes.
What is the form factor in the ideal case of λ/4 gap when you not include the λ/4 gaps?
When we don't include the air gap in the analytics, is 1.
But in the modeling, numerical modeling?
In the numerical modeling, it will drop to 0.95 or something like that. Yes. So in the experimental results, we tested this idea experimentally. So to test experimentally this idea, we fabricated 2 cavity resonators. They are pretty much similar. One of the prototypes that we made contains the air gap equal to 0, and the other one has the air gap close to the idea of λ/4. And they have the same design. We have all the wires, 10 by 10 wires aligned inside the cavity. The cavity walls are made by printed circuit boards. And we have a fixed port at the top of the cavity, which is a monopole antenna. It will excite an electric field that is parallel to the wires in our cavity. And to check the field homogeneity in the transversal section, we have a port number 2 that consists on a monopole antenna again, but this time this monopole antenna is flying. It will be scanning our field through some pre-drill holes. So it will be scanning in our field in the transversal section. So the idea to measure the electric field is to measure the S21 parameters or the different holes that we have in our cavity, in our 2 cavities, in the 2 cavity prototypes. With this idea of the experiments, we get we get the following results. So a first result can be the S21 parameter when we have the flying antenna located exactly at the center. And this is the result that we can have here. In addition to the experimental results coming from the prototypes, we have some simulation results made in CST, which have the same conditions as the experiment. Yes, so we can see the following behavior. We can see that in our λ/4 shifted cavity, the resonant frequency is red shifted with respect to the G equal to 0 case. That's one of the details. The other detail is that directly we can see the field monitors from the simulations, and we can see that in the transversal section, this fundamental mode has a quasi-uniform field for this configuration. Here we also have side results about the higher order modes. All of them are the transversal sections, and of course, these transversal sections are in regions in which we don't have nodes. So here we have the TM001 with a variation, one node in the Z direction, here with two nodes in the Z direction, and then the other higher order modes with this detail that the X and Y components are coupled. That's why we have this superscript C in the results. Yes, so we are predicting here the behavior expected before by the analytics in considering the resonant frequencies. And the second result that we have from the experiments is that we can measure or estimate the field homogeneity. So in a first case, to the left, we have kind of the sinusoidal profile with form factors around 0.64, 0.61 coming from the simulations and the experiment. And in the second case, in our optimized cavity, we have higher form factors that were obtained from the field scanning approach that I presented 2 slides before. There is some side results, even though the mode that is important for the application is the fundamental one, because that one has the highest field uniformity, and that one is the relevant for the axion detection. The higher order modes can be interesting because these cavities have been proposed to detect other particles like dark photon, another candidate of dark matter, or they have been also proposed to detect gravitational waves, in which the conditions of the modes needed to detect these fundamental physics are different, maybe not the fundamental, another one. So we decided to make an analytical study of the higher order modes. So in the higher order modes, we need to consider the effective wire medium with the spatial dispersion effects, because we are allowed now to have variations along Z. We need to consider the fields with a general approach. Our fields will depend on 3 coefficients, L, M, N, indicating the nodes along the 3 spatial directions. These F, G, and H, basically, as we have the cube cavity, actually cube cavities, these are indicating cosine or sine function depending on the mode that we are targeting. And we again need to take into account or need to check the dispersion relations in the different regions. So we need to check the dispersion relations in the wire media. We need to take check the dispersion relations in the air gap region. And in this case, we need in both, because X and Y are not the same anymore, because before we were focused on the fundamental mode. Now we are free to get other kind of modes, so they can be different in the X and Y direction. And the dispersion equations will look similar, but will allow us to get these components, particularly X components and Y components. This T stands for X or for Y. And it will depend on the the dependence of the field along every direction. If it is an even function, we use this dispersion equation. And if it is an odd function, we use this dispersion equation. So this is basically the higher order modes. It's like the same idea as the fundamental mode with some extra details, including by these coefficients L, M, and N, talking about the more variations of our electromagnetic field inside the cavities. So we have this behavior, for example, this chart about how the air gap is influencing our TM modes. So we can see that our fundamental mode is going to be a TM000 resonating at the plasma frequency. And considering the higher order modes, we have a similar behavior. They start to decrease the resonant frequency and go to more uniform modes in comparison to the ones in which G is equal to 0. And if we check the field profiles of these modes, we have this behavior, kind of good agreement between the analytical and numerical, with the exception of some particular modes. This is a limitation of the analytical model, is that we cannot predict coupling between the X and Y dependence of the fields, particularly in this TM200 and in this TM020, we can see just dependencies right in the X direction or in the vertical direction. But actually, when we are adding that air gap region equal to λ/4, there is a coupling due to these corners that we didn't consider. So the current field is actually not with just variation along X, not with just variations along Y, but a linear combination of both. So we have two modes that are different to the ones predicted by the analytics. And that's the detail. So we can also apply this idea to a cylindrical cavity. In the cylindrical cavity, actually, the problem is simpler than the square cross-section cavity because we are going to have just dependence of our field in the radial direction. So we will have this problem. We will have a region number 1 in which we have the effective wire medium and a region number 2 in which we have the air. And at the end, everything is bounded by a perfect electric conductor. So instead of the cosine and sine functions, now, as we are in cylindrical coordinates, we need to use the Bessel functions, and the same idea, focus on the fundamental mode. In this case, we need to use for the region in the air gap, we need to use the Bessel function of the first kind and the second kind. And also we need to satisfy the boundary condition at the metal, at the other. So it is already satisfied by this expression. And if we take the derivative, we can get the magnetic field. And the same idea as before, we can obtain a wave impedance that will experience our effective wire media. And we can obtain, this time it's depending all in the Bessel function, so it will change a little bit the analytical results. And we can get also a dispersion equations to get the resonant frequencies of our cavities, also considering the dispersion in the wire media region and in the air gap region. So the results for this analytical model in the cylindrical cavity are the following. We can see this behavior for the wave impedance. We have the same idea that at 0 is perfect electric conductor, and there is a value close to λ/4 in which we are going to have the perfect magnetic conductor boundary condition in the wire media. In comparison, considering the resonant frequency, we are going to also have a similar behavior. There is a value in which we can get the resonant frequency of the plasma equal to the plasma frequency of the wire medium. And if we consider the form factor, we see also an increment of the form factor in comparison to the typical case with respect to the optimal case in which the air gap is equal to λ/4. Yeah? So those are some preliminary results. There are some challenges here because Previously, in the square cross-section cavity, the unit cell was also square, so everything fits perfectly to have a perfect number of cells inside the cavity. This time, as our cross-section is circular, it's a bit challenging to define exactly where we are gonna stop our wire media, exactly where we are gonna define this first boundary, right? It is a challenge, and in this case particularly, our lattice is triangular. It could be more challenging even if we consider a square, right? But we can see that the results are pretty much in agreement between the numerics and in the analytics. There is
Jim, can I ask the question? Why is the results for numerical modeling of the form factor for physical wire media is corresponds very good than in other cases in the region near to lambda over 4. In the case of G equal to 2 or 4, the shift between the analytical one and numerical for physical wire media is much bigger than in the case of G equal to lambda over 4.
Thanks for the question. I think it's a great question. And we can see some details here about these physical wire media results. Before, when we checked the plasma frequency, everything was the same, like in the physical, in the effective wire media numerics and analytics, in the resonant frequency, everything was the same below the lambda over 4 distance. Now we have a challenge with the numerical physical wire medium, and that challenge is related in the sense that we don't know where to define that boundary of the wire media. It's not totally clear. In the other case, we have a rectangular lattice, a rectangular boundary. Everything look more intuitive. We didn't have a period to bound the wire media. In this case, we have a triangular lattice, and we need to end that triangular lattice in a circular shape. So it's not exactly perfect. And we see here in these results that it actually will be influenced by the air gap. Yeah, so that's why in some regions we have better agreements than in the other. There is like not a specific definition where to put this initial boundary of the wire media, where to put this initial boundary from which we are gonna start to introduce the air gap. There is not an analytical formula to do that, neither either a numerical one. So we just need to test the values, but yeah, it's a good point. Where to define that boundary condition of the wire media when we want to limit this boundary as a circle, right? Because actually, if we check the actual boundary, it will be something different to a circle because we have a triangular lattice. And another side result is related with the measurements of the plasma frequency. The measurement of the plasma frequency in a hexagonal cross-section cavity filled with a honeycomb wire medium. So the structure is the following. In those plasma haloscope experiments, we don't know 100% the mass of the axion. So it means that we need an experiment based on a cavity that is tunable. We need to tune that plasma frequency. We need to change that plasma frequency in order to sweep several possibilities for the axion mass. So one strategy that we propose is to tune that plasma frequency by using a honeycomb lattice, the deformation of a honeycomb lattice wire medium. So this deformation will consist on changing this R parameter. So this R parameter will indicate, for example, in a first case, that our wires are really close to each other. Our 6 wires in the hexagonal unit cell are really close to each other. And in another extreme cases, they are far apart each other. So it will create a tuning of the plasma frequency above 70% or in percentage, comparing the highest case in comparison to the lowest case. So the idea is that making the mechanical prototype about this structure would be challenging, and it will take a lot of time. So we decided to measure that it effectively, we decided to create a measurement strategy to test that effectively we are achieving this range of tunability for this structure. So the strategy that we propose is analyzing this honeycomb lattice inside of our cavities, in the wire media cavities, particularly optimized with the air gap here called delta capital. So we have the following scenario. If we check the resonant frequency, we can compare this infinite wire media, which will coincide with the plasma frequency value. We can compare with two cavities, with the lambda/4 shifted cavity and with the regular one. The regular one doesn't include any air gap, anything. So we can see that the regular one is always resonating slightly above the plasma frequency. But the lambda/4 shifted cavity is almost always coinciding with the plasma frequency. So this optimized cavity with the lambda/4 gap can allow us to measure actually the plasma frequency of our wire medium. And if we can measure the plasma frequency of our wire medium, we can corroborate that effectively with this structure, with this honeycomb deformation, we are achieving a tuning of the plasma frequency. If we check this side results about the form factor, and the form factor, we can see that, for example, here is a difference that was a question before. The infinite wire medium indicates an ideal case in which we don't have air gap. It includes the highest form factor because it has the highest field homogeneity. But the lambda/4 shifted cavity is approaching this value actually, right? It's not the same because it is including the air gap. And if we consider the regular cavity is slightly lower, the values of form factor always below 0.7. Yes, and the quality factor is not drastically affected by this introduction of the lambda/4 air gap, and it has the values similar to the rectangular cavity.
Jim, I have a question about the previous slide. It's interesting that adding a lambda/4 air gap affects on the form factor, and the form factor is better than in the regular lattice without air gap. But the Q factor is bigger than in the case of regular lattice and infinite wire medium. What is the purpose of it? I know that there is maybe no connection between these physical terms, but it's interesting that one curve is at the center, of two others, and as a second case, it's higher.
Yes, actually, it's an interesting question. These results, all of them come from numerics. They are numerical results. But yeah, in the numerical results, for example, if we are talking about the infinite wire media, if we are talking about the quality factor, it's a little bit hard to define because it's an infinite structure, and it's supposed that the quality factor is quantifying the energy stored divided by the energy dissipated. The energy dissipated in this case looks evident because we have the wires, so we have some currents flowing by the wires, and there will be some power dissipated due to those wires. In the cavities, it's more evident because we have the power stored. We actually calculated analytically for the rectangular cavity, and we can get some results that can be compared with numerics. In this case, we have identified always in the cavities that they look kind of similar. Those quality factors, they are not changing dramatically, indicating that the power stored is kind of similar when we are comparing it with the power dissipated. So the two sources of power dissipation are the currents in the wires and the currents in the cavity walls. Look like this ratio between energy stored and energy dissipated is kind of similar for the cavities.
Okay, thank you.
My pleasure.
And I also have a question. When you tune the plasma frequency of by changing the distance between the wires, you need to simultaneously change the shift between the wire media and the walls.
Exactly, that's right. Yes, that's right. And it is actually one challenge that we should address in the next works. Try to make a boundary that can be also tunable with this tunable plasma frequency, or if we leave a fixed air gap, we can optimize this air gap to satisfy the lowest wavelength, or the resonant wavelength, so it will improve slightly the highest wavelength. It will improve slightly, but not too much. And it will improve, of course, the lowest, because it will be optimized for the lowest. But now it's fixed. So yeah, we should create a strategy which allow us to maybe mechanically moving those cavity walls, which looks challenging, or just tuning this boundary by other means.
Yeah, but you have used high impedance surface with some electrically tunable high impedance surface.
Yes, that could be interesting. Actually, that's an idea that we are planning to explore, maybe the use of meta surfaces to try to tune easily that boundary there. Yeah, there will be a talk actually. 2 weeks after this, there will be a talk about that topic. It's interesting.
Thank you.
Pleasure. So we measure experimentally again with two prototypes. One prototype in which the wires are close each other, and another configuration in which the wires are farther apart, in order to measure the tunability between these two prototypes. The prototypes are pretty similar to the ones I showed before. Now we are not measuring field homogeneity anymore, because we already tested in the previous idea that the field homogeneity is working. So we are mainly focused on the measurement of the plasma frequency of these two wire media that we have inside these cavities. So the two-port system, these times we have two fixed ports. They are again monopole antennas to excite the modes, the TM modes, which have the electric field parallel to the wires. And the results are the following. Again, we are also getting some simulation results from the ideal conditions of the experimental prototypes. And we can see that effectively this fundamental mode looks uniform in the field monitors of CST. And in the experiment, we can check also that we effectively have a drastic change in the plasma frequency from 3.750 to 7.285, indicating that we have a tuning range above 60% for this structure. Yes, there were some limitations in the experiment. For example, we were not able to mimic the ideal case in which the wires are totally close to each other, because it will be difficult to solder them after that. So we chose a case that is a little bit lower. That's why in the analytics, we get like 70%, and in the experiment, 60% of that percentage that was promised by the analytics. And some conclusions and perspectives. So the conclusions are the following. We can improve the field homogeneity of our wire media field cavities, introducing the air gap equal to λ/4. In addition, the electric field profile can be actually manipulated. We can change the locations of the maxima of this field profile inside of our wire media cavities. And on the other hand, this idea of including air gap equal to λ/4 is useful also to measure the plasma frequency and to demonstrate the tunability, for example, of some structures that have been proposed to tune the plasma frequency of a wire medium. These are the two main conclusions that we have from this talk. And if we see the perspectives, we have the following. All the prototypes that are proposed in these wire media field cavities needs to be tunable. They have different strategies. For example, this one consisting in two lattices, and the tuning mechanism is mechanically changing the position of this set of wires. It will introduce some extra details for the lambda/4 idea boundary, like we don't have symmetry, right? Before everything was symmetric, we have a square cavity. Now we have a rectangular one with different population of wires. It will create some challenges there. The honeycomb lattice that we already discussed, another unit cell consisting of rounded wires which are rotating to create a tunability. This one also contains details of anisotropy, so maybe the idea that we propose can be used to actually measure the plasma frequency of this structure, because it looks more challenging in this case, in which we don't have the typical circular cross-section wires, but we have this other shape, more complicated. So it will be difficult to match with the analytics. And other novel designs consisting, for example, in the relative rotation between two sets of wires, in which every set of wires is following a spiral. This also can be challenging because it's not evident an analytical model to predict the plasma frequency of this structure. So our experimental strategy can be tested to measure the plasma frequency of this structure. And another detail with this tunable structure is that we have a range of frequency. We already mentioned that detail. So the air gap is fixed. It's also interesting to analyze strategies to try to tune that air gap length, or it could be with metasurfaces or with some mechanical means. And here we have some ideas that come from electromagnetic paramagnetic resonance. They were also interested in achieving a uniform field, particularly along the axial direction, because they place the sample there in the center of the cylindrical cavity, and they want a B1 field that excites the spins along the whole axial direction. So if we don't have field homogeneity in that axial direction, the performance of the electromagnetic paramagnetic resonance will be reduced. So they look for a uniform field in the axial direction. And they actually are using the same idea to achieve the uniform field. They are using an epsilon near zero media. Particularly, this epsilon near zero media is obtained here by using a metallic waveguide working in the cutoff frequency, under cutoff frequency. So it allows us to get a uniform field in the axial direction. And what they do in the endings to achieve that lambda/4. For example, they modify the cross-section to achieve this lambda/4 condition. They use some rings to achieve this lambda/4 condition, or they use also a dielectric to optically achieve this lambda/4 idea. So these are ideas that have been proposed in this context and can be also considered in our context of the wire media field cavities. Of course, in our case, it's a bit more challenging because we are focusing the transversal section and they are focusing the endings just in the single direction, the axial one. Yes, so that's the idea. And this is it. Thank you so much for your attention.
Thank you very much, Jim. Colleagues, if you have any questions, you're welcome to ask.
Yeah, Jim, thank you. I have a question regarding how you calculate this filling factor, the homogeneity of electric field. In the case of our medium, you have multiple metallic wires. inside each wire, electric field is simply equal to 0.
0.
And in a close proximity of each wire, also electric field tends to 0. So maybe it is not very well shown in the 1D plots you presented, because most probably your cross sections were exactly in between of the wires. Yeah. So these ripples, yeah,
Yes.
are due to the fact that somewhere the point of observation is closer to the wires, and in some cases it is further from the wires. But there is no point where you cross the wire itself. If you change this cross section, you probably will drop down to 0, right?
Exactly. It will drop totally to 0.
Okay. So my question is, your final homogeneity value of, let's say, 80% or something like this, does it take into account this
Yes, of
this
course.
wire proximity regions?
Yes, of course. It takes into account everything, the wires and also the air gap, which is a detail that maybe it's not so evident, but yeah, it considers everything. The drops of the field in the wires and the air gap region also.
Okay, thank you.
My pleasure.
Jim, I also have a question about the cylindrical cavity. In that case, you have shown that the maximum of the homogeneity of electric field is not when the gap is equal lambda over 4, but the gap is slightly more.
Yeah.
What is the purpose of it? Because there is no fringing or corner effects, and I suppose here the maximum should be more precisely equal to lambda over 4 if you...
Yeah, it looks like that. It looks like a one-dimensional problem because we have just the dependence on R. But at the end, when we got the lambda over 4 condition, we had the ideal case in which we have a plane wave incident to a perpendicular boundary. Now we don't have this ideal condition, we have a circular boundary. So it is imposing that analytically we are getting these Bessel functions and the roots are slightly changing to the lambda over 4. Yes. So for example, in the 1D case, it can be easily understood that this lambda over 4 idea, what is doing is the following: the plane wave, so will travel a distance in the air gap region, then it will bound in the cavity wall, and then it will travel another distance, and it creates that at the end it's a phase shift of 2 pi. So it is not changing anything in the wave that is coming back. But in this case, we cannot do the same analogy because we have a rounded boundary, so we don't have the incidence of the one-dimensional case.
Okay, thank you.
Pleasure.
Okay, maybe some questions from Zoom. Okay, I suppose no. So we will finish for today. Thank you, Jim. Another time. Let's thank the speaker.